Okay, in this video, I want to start talking about solution techniques for a two-sample hypothesis test. Let's go ahead and look at this problem. An investigation of the effectiveness of an antibacterial soap in reducing operating room contamination resulted in an accompanying table. So essentially what we have here is various rooms within a hospital and the before and after results. So the new soap was tested in a sample of 8 operating rooms in the greater Seattle area during last year. At a 5% significant level, can we conclude that the contamination measurements are lower after the use of soap? So what we want to try to prove is that after we use the new soap, did the contamination go down? In other words, is after the sample average of after less than the sample average of before? Okay, so let's go ahead and open up the starting file for this particular problem. Okay, we have the starting file here. We have the table of those before and after results and whatever metric they're using for assessing what the contamination level is. Let's go ahead and document what we know in this particular problem. We know that the alpha value is going to be 5%, 0.05. Okay. We need to try to identify a keyword in this particular problem, and I always recommend identifying that keyword and then letting that guide what hypothesis statement you're actually going to write. Okay, so the keyword here is lower. Okay. So the keyword is lower. And in these particular problems, what we're really doing is comparing two different samples. Before, in a one sample hypothesis, we normally had a value that we were comparing against. So we had some sort of survey result or a sample of new information, and we wanted to benchmark that off of an existing parameter. Here we're actually comparing two samples together. The keyword, again, is lower. So what that means is we're going to want to write a left-handed hypothesis statement for the alternative. So this implies a left-tailed test. Okay, so we have that left-handed test we'd like to write. I would like to make a note. You could actually write a right-handed test, but if you use the convention that I'd like to try to teach you, you always match the keyword up with the statement. And so some sort of statement, we have a HO and a H1. The alternative hypothesis must be a left test if we're going to use that convention that I would like you to use. So we have to figure out which mu goes where in terms of what makes sense. We want to prove that it's lower. So what we want to say here is that the let's say mu after is less than mu before. Okay, this would coincide with a keyword of lower, and it would keep this as a left-tailed test. Okay. Let's go ahead and finish the right-tailed test. Mu after is greater than or equal to mu before. Okay, so if you're having a little bit of problems understanding why I wrote the hypothesis statement this way, let's go ahead and look at the formula sheet. So we are comparing two samples, so we're in the two sample section of the formula sheet. We have a keyword of less than, so we know it's going to be a one-tailed test. And you might be thinking, oh, well, we have two samples, don't we have two distributions? We actually do, in fact. And the reason why I bring this up is that we wrote initially the hypothesis statement like this. Hypothesis, the null is mu1 is greater than or equal to mu2, and hypothesis alternative is mu1 is less than mu2. Well, which one is mu1? Which one of these is mu2? Is after mu1 or is after mu2? Which one? Well, again, I like to match it up with that keyword, and the only way that this makes sense based on the alternative is that after is less than before. So anyway, back to the conversation of having two distributions, because we have two samples now. What we can actually do is rewrite this way of writing the hypothesis statement by subtracting mu2 from both sides. So if we subtract mu2 here, we would be left with 0. And if we subtract it from here, we'd have mu1 minus mu2, which is exactly what I wrote here. Instead of putting a value of 0, here I wrote value. Now that might be confusing, but all this means is it's going to relate to how Excel actually asks you this question. Value normally is always 0. However, if you wanted to test the difference of it being greater than or equal to a different value, maybe you want to see if the difference is greater than 2, greater than 5, greater than 100, whatever it is, you can actually put in a value in Excel. For our purposes, we're going to use 0. So anyway, we can rewrite that hypothesis statement, and I'm going to do that after I copy this picture over to our spreadsheet. Okay, so I'm going to paste that here, and I'm going to rewrite this statement. I'm just going to say, or the alternative way to write this is H0 is mu after minus mu before is greater than or equal to 0. The H1 is mu after minus mu before is less than 0. So to me, this way makes a lot more sense because it actually mimics the figures in the formula sheet. Now we're really dealing with two samples, but what we're really saying is let's subtract after minus before, and we're dealing with one sample at that point. So let me just go ahead and create a row here, and I'm going to write difference. What we're actually doing is investigating one distribution after we take the difference. Now, this is a great opportunity to start talking a little bit more in-depthly about this particular problem. This is, in fact, a paired test, meaning the before and after results are all paired to a certain room. That is very key, and it's the only reason that I can take a difference of this column, these two columns, I should say. So just be aware of that. That's a very important aspect of this particular problem, is that it is paired. The results before and after, both in this row, relate to a specific room. So normally when we talk about paired results, it's paired to a room, maybe it's paired to a person. Maybe I am testing the effectiveness of a drug, and I want to track your vitals before you take this drug and track your vitals afterwards. And I want to see if there is a noticeable difference, or something has increased or something has decreased. Well, that all relates to this concept of a paired test, and that's exactly what we have here. We have a paired two-sample test, and we're going to test the mean. Okay, so let's finish this formatting here. Now, you might be wondering if this thought process or the strategy of solving this problem is similar to a one-sample test, and it really is. We could calculate the mu for before, average, and we could calculate that for the after and the difference, and we could actually go ahead and calculate the standard deviation of this sample. And I'm just filling out the formulas here. So we could definitely do all those types of things. We're definitely going to have to calculate a critical value and a critical region. However, once we start talking about two samples, it's much more difficult to calculate those statistics than it is for a one sample test. Let's take a look at that formula sheet again, and I'll show you what I'm talking about. Well, the first thing after we skip the portion about which way should the hypothesis be written, we come to a decision tree. And this decision tree I created so we actually know what case we're talking about, and the cases here after this decision tree relate to these cases in the table. Okay, so let's just talk through this. Are the samples independent? In fact, in this particular problem, they are not independent. Each sample is dependent of that room. So they all can relate back to that room. In other words, if I was to sort this list without respect to the after, then the whole analysis is sort of bogus. I have the before of room A and I have the after of room A. So these two values are dependent upon which room they're coming from. So that's what that means. So these are in fact dependent samples if a case, if the two samples are in fact not independent, so in other words they are dependent, we're going to have case A. Now let's look at case A. Case A, when we're talking about calculating the statistic, the test statistic, to make a conclusion on our hypothesis, we have case A, that means our samples are not independent. I wrote this here as to stop. This is, we have concluded that we are going to use this row of the data of the formula sheet. Other conditions might be B and C and D and so forth, and the way you should read this is I'm going to look left or right, and when I see a no, the first time I come to a no, as long as there's not a no underneath of it, you're going to pick that test. So we'll cover some of those examples later. Let's focus on case A. This test will be a t-test, especially that we only have 8 samples. The test stat is calculated by the difference, the d bar divided by the standard deviation of the difference divided by square root n. So let's go ahead and calculate that. We have a t-stat, and I'm going to just call this manual, because I sort of have a surprise for you, if you will. Okay, t-stat is going to be the difference divided by, make sure you got your parentheses, standard deviation divided by, it's going to be 8. I'm going to go ahead and write a count statement and count how many rooms I have. That's going to return 8, so I can calculate that t-stat as negative 8.5. And you know that just sounded a little bit different or wrong when I said that. I forgot that square root, so we need that square root right here. SQRT count A, and let's go ahead and fix that. So we have negative 3.02. That sounds like a much more reasonable value. Okay, so that's our test stat. What about our T critical? Okay, so let's go ahead and look at our formula sheet. Down here at the critical value, we are talking about a t-test. Our direction is going to be the left. We've already determined that. So let's look for the t-stat left. Our critical value is going to be this formula. Let's go back and calculate that. Alpha is going to be equal to 5%. And degrees of freedom. Well, let's hold off on that just yet and go ahead and hit enter with putting this into a text form. The degrees of freedom is actually a little bit difficult to determine. Before this, if we're talking about a one sample test, it's always n minus 1. Okay, let's look at this table again up here. We have that case A has a degree of freedom DOF equals NP minus 1. Well, what does that necessarily mean? NP, we have this little note, the before and after results can be paired. That's the first star here for the no. And then the start on the DOF, number of paired samples minus 1. Okay. So let's go ahead and compute that DOF. We'll calculate here N and DOF. N will be count A of the number, which will be 8. DOF is the number of pairs, which is 8 minus 1. We have a DOF of 7. Let's copy this format and apply it here. And go back to our T-critical and take away the single quote and update the degree of freedom to 7. So we get this value. And I'm just trying to do some formatting, take away some decimal places. We have a T-critical of negative 1.89. Let's go ahead and draw this out so we can make a conclusion similar to what we have done prior. We have a normal distribution. We have a left-tailed test. Our T-critical is here. Our critical region is here. To the left of this, we're going to reject the null statement. If we're talking about over here, we're going to fail to reject null. So that is if we are on the right hand side of this critical region, if we are in fact over here. And that's all, of course, based on the test statistic. Now let's put the test statistic in. Our test statistic is -1. Our test, I should say the test critical is -1. Our test stat is -3. So it's way over here. Test stat. So we are in the reject null region. Okay, what does that mean? So let's make a conclusion. We are going to reject null. What does that mean? Let's go ahead and look at the null statement. We are rejecting the null, so we can conclude that the mu after, or the contamination measurement, is less after using the soap than before. So it's basically suggesting that the new soap has a positive impact on the level of contamination. So we are better off using this soap. Okay, so let's talk about this quote-unquote surprise I have. So we did this a manual approach. I want to go back to this spreadsheet and just show you that calculating the z-test, or not the z-test, the test statistic is not as always easy as what we just completed, nor is the degree of freedom. If we look at case B, case C, and case D, these formulas get a little bit more complex, and quite frankly, they're a little bit of a nightmare to accurately formulate in Excel. So what we can do is Excel has a nice feature called the Data Analysis Tool Pack, and we can go to Data Analysis Tool Pack and go to these tests. We have t-test paired, exactly what we want. But just to show you, we also have a t-test 2 sample assuming equal variance, unequal variance, and 2 sample for means when we're talking about a z-test when we know the population parameters. I'm going to select the paired because we definitely have a paired case here. Hit OK. It's suggesting, well, what is variable 1? Well, remember when I was going over the formula sheet trying to write the hypothesis statement, I said, well, what is mu1? What is mu2? Is it after? Is it before? So I'm going to treat this as variable 1 is the leftmost, meaning whatever you write here, mu after is going to be variable 1. It actually appears second in the list. Okay, so that is a little confusing and where most people make some mistakes. Variable 2 is going to be before. So remember, look at your alternative, after and then before. After minus before. That's exactly how this data analysis tool pack is going to calculate all those mean differences and the sign of the test statistic and the critical value. Okay, remember also when I said value, and I referred to this value here. Now in our case, it's 0 because we just simply minused or subtracted mu2 from both sides. Well, the analysis tool pack actually lets you put in any value you want. We want to put in a 0. I did in fact go to D12, which is a label in this row. Our alpha value is 0.5. Also watch this. Sometimes you can get in a rush and just hit OK. I'm going to put this report somewhere close to what we can see here. Let's go ahead and put this analysis, well, let's just put it right under here. I'm going to hit OK. I'm just going to call this alternative approach. And we're letting the analysis toolpack generate all these values. So just like when we calculated the mean after and before, those are calculated here. 5.58, 5.58, 8.7, 8.7. It's calculating the variance. The variance is not to be confused with standard deviation. In fact, let me put an extra row here. Standard deviation is the square root of this variance. So we can actually calculate that if you really want to, but we have the 2.6 up here, and 2.1, 2.1 on the before. So it's actually calculating everything we need. The hypothesized mean difference, we entered that as a 0. The degrees of freedom is 7. The test statistic is exactly what we manually calculated up here, negative 3.02, negative 3.02, and it actually calculates the p-value for us, which is great, and it actually provides us with the results of both a one-tailed and a two-tailed. What I would recommend is that if you know you're dealing with a one-tailed, just block out this information so you don't look at it, because we're not analyzing a two-tailed situation. Excel doesn't know that. Excel didn't have a field that says, well, are you testing one-tailed or two? So we have to know what tail we're testing and then interpret the right results. The test critical is 1.8, and this is where things get a little confusing when using the tool pack. The way that this is implemented always shows you the positive, the absolute value of the critical. We have to know that we are actually testing the left tail. This, in other words, will always be positive. Even though we adjusted for after and before, we got the right test statistic. That's fine. But I'm telling you, Excel will only give you the positive test critical. So we have to know that. If I was doing an analysis, I would simply go in here and say minus, just so the table has been updated. And you might even make a note, updated to reflect left tail, something like that. So anyway, you might want to put in that note. The interpretation is exactly the same. The critical value is negative 1.8, so it's close to the center, which means our test statistic lies far on a tail. If it's far on a tail, our p-value must be 0. If our p-value is less than alpha, we reject the null and accept the alternative. So we can actually do this either way. We can do it through the manual methods, or thankfully we have the software that can implement this. Again, it becomes more of an issue when we start looking at other cases, and those cases get difficult to calculate things like the test scores and the critical values and so forth. Now the cases will come into play later when we solve other problems. For this case, we are talking about a dependent paired test. Most tests are not, so you'll be in one of these cases, B, C, and D. Now, the only difference is the first thing you want to ask yourself, is the population known? And this is variance, but if you know the variance, you know standard deviation, and if it's known, you use case B. Case B relates to the z-test. Now, let's say the variances are not known. Then we just simply ask, well, are the variances equal? And if we say that they're equal, we're meaning that they're coming from the same population, and this is C. And if they're coming from the same population, we do this fancy calculation to pull the variance together to get a better idea of what the test statistic should be. If the variances are not from the same population, then we use the final case, and we adjust for that calculation here. So anyway, we do have the software. You will not be asked to calculate these manually.